All right, hello and welcome to your next video about chemical reactions. I've gotten some questions recently. People have been emailing me and asking me, hey, where do you store all of these great dad jokes you tell? Well, the answer is in a database. That's a D-A-D, data, you get database. Okay, I'm sorry, I know. Okay, calm down. It was bad. I know, but it's okay. We'll make it through this. All right, let's talk more about chemical reactions. So this video is a review of two things. One is figuring out types of chemical reactions, and the other is balancing chemical reactions, chemical equations. So as a review, I told you that there are 5 major types of chemical reactions, and now I'm giving you some hints as to how you can figure out which ones they are. So the first kind is synthesis, and synthesis is putting together. So one way to find out that you have a synthesis reaction is the product compound. So one of the ones on the right side of the arrow is bigger than the reactants. It's more complex. There's more elements to it. And then decomposition. So decomposition we can usually tell because there are, more products than reactants. More products than reactants. So that means there's more things on the right side of the arrow than on the left. So usually you have one bigger molecule or compound on the left and more than one on the right. Combustion. A good way to tell combustion is that carbon dioxide and water are the products. So combustion leads to carbon dioxide, water, and then usually energy. That's the point of combustion. There's also oxygen on the left side. It's a reactant in combustion, but because oxygen is a reactant in multiple kinds of reactions, I didn't want to put it there as a key, although you are going to see it in combustion reactions. Single replacement, that's where you're going to see one element and a compound react. So it's like one plus or one element plus a compound of 2 elements gets together, and then they kind of switch. I'm trying to do the old math trick. I'm not good at it. They switch places, and then in a double replacement, it's like a do-si-do. They completely rearrange, right? So 2 compounds react, and everyone switches places. So let's look at some examples. What type of reaction is this? So we've got NaBr, that's sodium bromide, and BaCl2, that's barium chloride. They react together. The products on the right side, they are NaCl, or sodium chloride, and barium bromide over there. So when they react together, this is what we form. So what kind of reaction is this? So what I'm looking at is I've got 2 compounds on the left. 2 compounds, and then on the right I've got the same elements rearranged into different ionic compounds. So what this is telling me is that everybody is switching places, and when everybody switches places, that's a double replacement reaction. Double replacement reaction. Okay, next one. Try this one on your own first before, and then pause the video. So we got magnesium and hydrochloric acid reacting together to form magnesium chloride and some hydrogen gas. Pause the video, try it on your own, and then let's see. Okay, so what you should have seen, hopefully, is that magnesium takes the place of the hydrogen. So these two swap while the chlorine is always part of a compound. So 1 takes the place of 1, right? Giving us magnesium chloride and this hydrogen gas. So that is a single replacement. So that's 1 took the place of 1, right? That's a single replacement reaction. Next one to try. Okay, looks big, but this is actually not that complicated of a reaction. C6H12O6 right here, that's glucose, plus oxygen, and the products are carbon dioxide, water, and energy. Pause your video, see if you can figure this out in your notebooks. Okay, welcome back. So what do we have here? We have something kind of big over here. We've got oxygen as another reactant, and then our products include water and carbon dioxide. Water and carbon dioxide. Remember, I said if you've got water and carbon dioxide as your products, then that means you are looking at a combustion reaction, right? So this is actually something you're going to see a lot of in biology next year, and that is your glucose molecule right here is burning in the presence of oxygen, and it gives off carbon dioxide and energy. And that's actually the main reaction that's occurring in the mighty mitochondria, the powerhouse of the cell, right? So your body is doing this right now. It's taking food molecules and it breaks them down into simpler molecules. And then this glucose, which is very simple sugar, gets fed in, uses the oxygen in your blood that you got from breathing to burn these molecules, producing energy that your body can use. And then the waste products, the waste products are carbon dioxide and water, which your body is then trying to get rid of the excess, right? That's why you breathe out, and out of your breath comes carbon dioxide and water, and of course water comes out in other places. Okay, let's try this one. Mg plus N2 gives us Mg3N2. So this is magnesium, and nitrogen gas gives us magnesium nitride. Pause the video. Try this one in your notebooks. Okay, so hopefully what you saw here was that you have more things on the left, fewer things on the right, and you have a more complex, a bigger molecule on the right than you do on the left. So this is a good example of a synthesis reaction, right? We took two simpler things, two things in this case in their elemental forms, and we stuck them together to make something more complex, magnesium and nitride. All right, here's another example. NO2 breaks down to N2 plus O2. N2 plus O2. Pause the video, try this one in your notebooks. Okay, so welcome back. In this example, we have a more complex thing, so something with 3 atoms in it, breaking down into simpler 2 atoms each here, and then these are elemental forms of these two things, nitrogen and oxygen. So this should be a decomposition reaction. And in fact, this is something that happens in your car when you drive. So one of the things that happens as you burn gasoline in your car is you produce a bunch of pollutants that are pretty bad for our air quality and pretty bad for us to breathe in. So your car has something called a catalytic converter in it. Catalytic converters have been around for a while, and what happens is all the nasty stuff coming out of the burnt fuel, the used fuel vapors coming out of the engine, get fed through as part of your exhaust system, a catalytic converter, which contains a bunch of metals that help speed up these chemical reactions. And so, among other things, the nitrous oxide, or NO2, nitrogen dioxide is its proper name, gets broken down into N2, which is nitrogen gas, which is what most of our atmosphere is made out of, and oxygen gas, right, which we breathe as well. So that is one of the ways that we break down pollutants. Still not necessarily great to be pumping this much nitrogen out into the atmosphere, but better than having to breathe in all of this stuff. Okay, here's another one to try. CO2 plus H2O, notice they're on the left side, plus energy, gives us C6H12O6 and oxygen. Pause the video, try this one on your own. Okay, welcome back. So hopefully what you noticed was you have 2 relatively simple molecules here, carbon dioxide and water, and then you end up making this more complex thing here, the C6H12O6, which you might remember I told you is actually a glucose molecule, a simple sugar. And so this is synthesis. This, in fact, is the exact opposite of the respiration. Sorry about that. Exact opposite of the respiration equation that I gave you before. So this is photosynthesis. You've got carbon dioxide and water getting fed into the plant, and then using the energy of the sun, the plant makes glucose, right? It makes sugars that it then turns into more complex molecules to store up in its leaves and other places. And then as an output, it also creates oxygen, right? And that's why we get oxygen to breathe from plants. So this is a synthesis reaction that you will see in biology. Okay, and so balancing chemical equations, let's review a little bit. Remember, we write out the number of atoms of each element on both sides of the arrow. We change only coefficients. We never change subscripts. And we try different coefficients until all the numbers are balanced. So let's try some examples. So here is the decomposition of H2O2, otherwise known as hydrogen peroxide, and it turns into water and oxygen. This is actually the elephant toothpaste reaction. So if we write out our elements on both sides, we've got 2 hydrogen and 2 oxygen on the left, 2 hydrogen, and 1 plus 2 is 3 oxygen, right? So we've got an odd and an even here, which tells us that we're probably going to need to do some odd and even coefficients. So let's see. First thing that we could do is possibly tackle having too many or needing more hydrogen. So what we can do is, needing more oxygen. So what we can do is we can put a 2, that's the smallest coefficient we can add in there, next to the H2O2. And what that does is give us 4 hydrogens and 4 oxygens. Since that ends up with more hydrogens on the left than on the right, we add a 2 in front of this H2O, and then we end up with 4 hydrogen, and 2 times 1 is 2, plus 2 is 4 oxygens, and that very conveniently works out. So smiley face for that one, because we got it balanced. Same numbers on both sides means it's balanced. Another one to try. So this one looks a little more complicated. It's actually not that hard to balance. It just might be an unfamiliar set of things. So this is uranium oxide, UO2, uranium oxide, and then this crazy stuff, hydrogen monofluoride. And they will swap some places and make uranium fluoride and water. Uranium fluoride and water. So what do we have on both sides? We've got uranium, so that's the U, and we've got 1 on the left, 1 on the right. We've got oxygen, we've got 1, 2 here, and only 1 there. Hydrogen, we've got 1 here and 1, 2 here. And then the fluorine, we've got 1 on the left and 4 on the right. So we need all these numbers to match up back and forth. So what should we do? So one of the things that I like to do is maybe leave hydrogen and oxygen for the last and try other things first. So let's look at how our uranium and fluorine are doing. So the uraniums are matched. It's this fluorine we want to work with first. So there's 4 on the right, 1 on the left. Let's put a 4 next to this hydrogen. Okay, we put a 4, next to this hydrogen monofluoride. We put a 4 there, and so that gives us 4 hydrogens and 4 fluorines on the left. We haven't done anything to the right, so we've got 4 fluorines and 2 hydrogens. So now we just need to balance those hydrogens. Notice we have 2 hydrogens, we need 4. We also only have 1 oxygen, we need 2. So let's try putting a 2 in front of that H2O, and that works out quite nicely. Now we have 2 times 2 is 4 hydrogens, 2 times 1 is 2 oxygens, and that actually gives everybody a match. All right, let's try another one. So in this one, I left everything blank. You do the counts first. So this one, try it entirely on your own. Count up on both sides, try to balance it, and then come back for the solution. So pause the video now. Okay, so welcome back. This is boron oxide. No, that's a covalent compound. Sorry, diboron trioxide and hydrogen monofluoride, and then they flip places, creating boron trifluoride and water. So you should have first done this, right, which is count the number of each on both sides. And so we've got 2 borons, 3 oxygens, 1 hydrogen, and 1 fluorine here. And then 1 boron, 1 oxygen, 2 hydrogens, and 3 fluorines here. So interesting how this pattern goes, right? It's kind of flipped. This means we're probably going to have to use some 2s and 3s. So remember, my tip is, let's try everything but oxygen and hydrogen first. There's 2 ways we could approach this. One would be to put a 3 in front of the HF so that we can balance the F's, but I prefer to try these B's first. And there's not necessarily a better answer to either, but that's just what I tried to do. So we got B2 over here, we need a 2 over there, and that gives us 2 boron and 6 fluorine on the left. Okay, so that's a lot of fluorine. We're going to have to balance that out right away. So let's put a 6 right here next to the HF. What does that give us? 6 fluorines and 6 hydrogens. So our fluorines are balanced, our borons are balanced. Now we got to deal with the oxygens and hydrogens. Well, it so happens that if we need to get 6 hydrogens and 3 oxygens, we can actually put a 3 in front of the H2O, and we end up balanced, right? So hopefully that was relatively painless. All right, so that's it for review of balancing and review of types of chemical reactions. As always, email me your questions, and you got plenty to try on your own. See you next time.